Hello, this is Alex Gonzalez, and this is my Lab 3. So the purpose of this lab was going to be to find the magnetic moment of a bar magnet that we got, and we are going to be using two main equations throughout this. The first one was B bar equals KR raised to the N, and this is going to be used to find the K value and the N value, which will be used in other parts of the lab. And the second equation we used was K equals mu naught over 4 pi times 2 mu in order to find the magnetic moment of the magnet. So in part one of this experiment, we first started by finding where the best reading was going to be found on our phone. And we did this by finding the strongest values when we had our phone in portrait mode and landscape, and we put tape at those values to find where we are going to be getting a good reading. And from there, we found at what distances our phone would read 20 microteslas, 70 microteslas, and so on. And then we are going to plot those values into a spreadsheet given to eventually get a graph of that B bar equation, except the natural log of it. And then from there we were going to be able to find that K and N value that we were talking about earlier. And in the part two of the lab, we were finding the distance from the magnet at which we would get 100 microteslas reading at the net of all the values, and then that distance we are going up by that same distance and then reading the X, Y, and Z values there. So the calculations are mostly for that first part of the lab, and I found that the N value was going to be negative 2.8, and then the natural log of K was negative 13.922, and I did that simply by reading off the function for the graph that they had set up for us. And then from there I did have to do my own calculations and found that K was equal to 8.99 e to the negative 7th, and I did that simply by raising that natural log of K. I did e raised to that to find the actual K value. And from there I set up that equation I talked about earlier, and made it K equals mu naught over 4 pi times 2 mu, and solved for mu in that and found that mu was equal to 4.495. So the coding for this lab, it had, you make arrows for the magnetic field, 2 different sets, and then also the magnetic field of that 45-degree angle that we were doing in part 2. So in the first part, I just made a function for the magnetic field that I would go back to in most of these arrows that I made. And I had 4 cyan arrows and 2 orange arrows, which I'll show in the next slide. But basically, you just create it using that magnetic field equation, and then have it facing whichever direction it is pertaining to, and then also you're going to have it at different observation locations, which you had to put in. And then the 45-degree one is pretty similar, except there's a few more things added, and then it eventually does point in that 45 degrees. And then in the second coding section, I just show the picture of it, and I found in this that the B net was 3.41 e to the negative 5th teslas, but in the actual experiment, mine was 2.6 e to the negative 5 teslas at that 45-degree angle, which is a difference of about 10 microteslas, but that could be due to a lot of reasons in the lab. Like if there was wiring underneath me that might have messed it up, or I had my computer not next to it, but pretty close. So out of these statements, the first one is correct. I'm going to get a near zero measurement in the x when I move farther away. And the second one is not. You're going to get an increased magnetic field as you move closer. And the third is also not true, but the fourth is true, and I underlined the ones that were. And if I had oriented the experiment if I didn't orient the experiment to compensate for north, then I would have just gotten a answer that would be messed up by the Earth's magnetic field. And if I had stuck two together, I would have gotten probably 2 times my answer in most of the experiment, which would have messed it up.